After we discuss about the fuzzy logic, this video is trying to focus on how do we learn how to use the fuzzy C-means clustering to basically assign 1 point to multiple clusters if they see fit. So fuzzy C-means clustering is a method of clustering which allows one piece of the data to belong to two or even more clusters. And this is make it available through the fuzzy logic. This method is actually developed quite a few years ago, in 1973, and it basically has been improved in 1981. So this algorithm is about 40 years old. However, personally, I think this is a very powerful clustering method, and this one is actually what we call softly divided the whole data set into smaller pieces, and they will have a soft boundary instead of the crisp boundary, which means that 1 point can only belong to one cluster. So let's take a look at the ideas first. If we look into this example, we have 7 points in the two-dimensional space. In our K-means clustering discussion, you can easily see that 1, 2, 3 is forming one cluster, 5, 6, 7 is another cluster. The point 4 is kind of in the middle, and if we purely calculate it by the distance, node 4 will belong to the second cluster on the right side, which it actually have kind of somehow similar distance to the left cluster. And how do we really make a decision that which cluster that this one belongs to? So in fuzzy C-means clustering, instead of the node will belong to the shortest distance cluster, this algorithm is changing a little bit. What this algorithm is trying to do is very similar to K-means clustering. So it will start initially randomly decide 2 points, and then instead of finding the shortest distance and make it belong to the cluster, it will use the distance to calculate the membership belonging percentage. So you can see that node number 1 is much closer to node 2 and is very far from the node 6. And therefore, if we calculate it by the percentage, this one will belong to node 2 for 95%, while 5% to the other cluster. And you can see node 3 is actually 90% closer to node 2, and with 10% goes to the other side. While we looked into the node 4, you can see that this time, because it's slightly closer to node 6, so it will have 55% belongingness versus 45% to the left cluster. However, if we really do go through the whole percentage calculation, which we'll talk about the formula pretty soon, we can set up a threshold saying that as long as you are greater than, for example, 40%, then you do consider as part of the cluster. And therefore, you can see that in this method, we will be able to generate still 2 clusters, while node number 4 belonging to not only one cluster, but both of them. And this is the idea of the fuzzy C-means clustering. Of course, just like K-means clustering, it's not the end of it. You still need to calculate the center of the cluster and then recalculate, repeat the whole process until the center has not changed or stays in a certain distance. Therefore, this is the idea of the fuzzy C-means clustering. You can see it's very similar to K-means clustering. The only difference is the concept of the membership function. So if we want to look into the pseudocode of fuzzy C-means clustering, you will see a lot of similarities in this one versus the K-means clustering. Starting with the first step, you need to initiate a membership function matrix. Depending on how many data that you have, as well as how many clusters that you have, you need to decide your membership matrix. So for example, we will see a data set with 7 points, and we only cluster them into 2 clusters, and therefore you will need to initiate a 2x7 matrix to store all of the membership values. And then what you will need to do is that starting with the initial centroids, so that we will need to randomly decide 2 points, And after that, after the whole iteration is done, we will need to recalculate the centers. So this is the formula of how we can calculate the initial centers if we are not generated randomly. So once that is done, we know where do we want to start. We need to calculate for every single item what is their membership value belonging to the clusters, just like we see earlier. For node number 1, you need to calculate your membership to the first cluster as well as the second cluster if you only do 2 clusters. And you will repeat the whole process, finishing all the metrics of the membership, and then we will need to recalculate the center and then try to see does it change enough or not. So if it is stable, then we don't need to continue the modification. Compare with the k-means clustering. It's almost the same idea. And you can compare this pseudocode with the fuzzy k-means clustering. So in order to talk a little bit deeper about the membership function calculation, now let's take a look how do we do that through a real example. So you can see that this is the formula of calculating the membership function. Uij indicating that I is the node that you want to calculate it. J is the cluster that you want to look into. So you can see that in this example, we have 7 nodes. Node 2, 3, 4, 7, 9, 10, 11. So we have 7 nodes over here. To start the membership calculation, you can see that on the right lower corner, I have a matrix. It's exactly 2 by 7. This is indicating the end result of this calculation. So we're starting from the first one, Uij equals to U11, indicating for the first node, I want to calculating the membership to the first cluster. So you can see that the formula over here is indicating it's going to be 1 divided by this whole big thing. So what is this? This is trying to say that you put a sigma over here, k equals to 1 until the number of clusters. So in this example, we only have 2 clusters, so it will go from k equal to 1 and then k equals to 2. And then what we see over here is xi minus cj, indicating that I is the node that you want to look into. So the first node, in this example, first node is value of 2 minus cj indicating the center of the cluster. So in this example, it's 3. So it's 2 minus 3 divided by xi minus ck. So xi is still the number of 2, which is the first node that we want to look into, minus ck. You remember the k starting from 1 goes to 2. So in the first node, it will be c1, which is exactly the same value that we see for the first cluster. So it's 2 minus 3. And then that's not the end of it because we have a sigma over here. So we need to plus the same thing on the numerator. The denominator changes a little bit. So you can see that it's going to change into still 2 is the first node minus ck. K is now become 2, indicating the second cluster. So it's 2 minus 11, and which you can see over here. So this is the sigma of this value plus this value. You can see that here is a little bit power things over here. By default, we usually set up m equals to 2. So it's going to be 2 divided by 2 minus 1, which is still give you the value of 2. So you basically square the whole values that you want to sum up, and then basically you can see that this is the results that we will be able to get. So it will be 1 divided by 1 plus 1 divided by 81 equals to 81 divided by 82, which indicating that for node 2, it belongs to the first cluster with 98.78%. And therefore, you can see that we have this value over here. So that's how we can generate the U11 for the first item. The next thing that you can see is that now we want to do the U12, indicating for the node 1, what is the percentage belonging to the second cluster. By doing so, we use the same formula. So you can see that now it's become U1 and 2 over here. It's still 1 divided by the whole sigma things over here. K equals to 1 to 2. So it's not changing. And then xi, which is x1, node number 2, minus cj, because we are looking at the second cluster. See the U12, 2 indicating the second cluster. So you can see that for the numerator, will become 2 minus 11, and then divided by the first cluster, which is 2 minus 3 coming from the first cluster, plus the second part, 2 minus 11, still stays the same over here, and then xi, which is x1, minus c2, which you get 2 minus 11. Both of them give the power of 2. You will see that the percentage-wise is become 1.22%. You can see that is how we will be able to calculate the percentage belongings of those, and then you can fill in U11 and U12 over here. If we move on to the next example, node number 3, because it's itself, actually, at this case, you will see that the percentage of belonging is 100% and the other one is 0%. In the last examples, I want to talk a little bit deeper about this one, but for now, you can see that is a very straightforward percentage calculation. For node number 4, which is our third node, so you can see that we try to calculate the U31 and U32. The U31 equals to 3. Node number 3 is actually the value of 4. 4 minus the first cluster, which is 3. You can see that 4 minus 3 over here. And then sigma is going to be base the value minus the first cluster, so comes from here, plus the 4 minus 3 divided by 4 minus 11, which is xi equal to 3, so 4 minus ck, k equals to 2, so the second cluster at the location of 11. So you can see that that is the calculations. At this time, we will see the node 4 belonging to the node 3 for 98%. On the other side is 2%. You can see that this calculation will always give you a value of 100% if you sum up the two values. Now, let's look into the most interesting one, node 7. I want you guys to see this one. For node 7, to calculate the distance, to calculate membership from node 7 to first cluster and the node 7 to the second cluster, you use the same formula over here again. So to calculate for the first node, first cluster, U41 equals to 7 minus 3 over here, divided by 7 minus 3. And now we look into the other side, 7 minus 3 divided by 7 minus 11. So you can see that we keep the same value, 7 minus 3 over here, and then what we change is the denominator for the two clusters. In this case, you can see the value we get is actually 50% because it's right in the middle of the two. The other side will give you the same value, 7 minus 11, 7 minus 7 divided by 7 minus 3 divided by 7 minus 11, and then we will get another 50% over here. So this is actually giving you a 50 and 50%. Look into the next node, the fifth node, so U51 that we want to fill in. You can see in the node 9 is the fifth element. It's much closer to the right clusters already. So let's take a look what's going on. So to calculate for the U5, the number 1 cluster, we use 9 minus 3 over here, divided by 9 minus 3, and then 9 minus 11 on the other side. So we will get the 10%. On the other side, we will get 90%, indicating that this node belonging to the first cluster for 10% and 90% to the second cluster. Node 10 is actually closer to node 11 now, so you can see that we will become 2% versus 98%. The same thing, 10 minus 3 to calculate U61, 10 minus 3, 10 minus 3 divided by 10 minus 3, and then 10 minus 11. And then we can get the 2% versus 98%. So finally, when we comes to the last node, this is the details I want to tell you about. So you can see that for the node 11, in order to calculate the distance, you will see 11 minus 3 over here, and 11 minus 3. So this value will give you 1 plus 11 minus 11. This is the detail I want to talk to you. If you going to write a program, you will have a divided by 0 problem. So you need to have an exception over here. And that's why you can see the node itself is itself. So you have 100% versus 0%. But what I'm trying to say, if you write a program, you will have some divided by 0 problem over here. So this is some exceptions that you need to look into. So this video talks to you about how to calculate a membership. The next video is going to talk about how do we calculate the next centroid.